Hello everyone, guys. Good evening to you all. So I can't see many people inside. So let's wait for some time to check if somebody else joins. Okay. So I welcome you all to today's problem solving session. Probably we will start by discussing the assignment questions from the last week. That is your week 6 assignment questions. And then we'll take up some problems out of your week 7 contents. Okay. So let me share my screen. So let's start with your last week's assignment questions, and to check if you guys have some doubts on that, and you can ask me if you have any doubts regarding any of the questions from your last week assignment. So yeah, the first question says that which deformation zone in metal cutting operation is located around which region? Okay. So for your reference, I have shared this diagram with you. So as you can see that this particular interface, this is the chip tool interface. Here it is actually the secondary deformation zone. And this one at the shear plane, along the shear plane, we have the primary deformation zone. Okay. And the red portion here, you can see that this is actually your flank wear zone, where it happens that the plastic deformation happening due to friction between the tool and that of the workpiece. So that thing can be controlled, it is controllable. So this is the least one actually. And the major one happens to be the primary shear zone. Okay. So in this case, you can check that two options, option A and option D, can be correlated to this particular diagram representing the deformation zones in machining process. Okay. So option A and option D should be the correct options. Proceeding. The second question says the temperature rises in dash due to dash. Okay. So temperature mainly rises for what? Due to friction, right? Due to the rubbing action between two entities, isn't it? So you can have a rubbing action between the tool and chip, between the chip and the workpiece at the shear zone, okay, then between the tool and the workpiece. So from the given options, you can see that primary and secondary zone, deformation zone. Okay, the first option says temperature rises in the primary and secondary deformation zone, and due to plastic deformation of metal in the shear zone and the friction between tool and chip respectively, right? So obviously, this can be considered. Now, the second option says primary and secondary deformation zone and friction between tool and chip and rubbing action of tool with workpiece. Okay, so that is not right, because primary deformation zone is not between tool and chip, rather it is between the tool and the workpiece at the shear zone, right? So option B is not right. And then option C says the rubbing action of the tool with the workpiece and the plastic deformation of metal in the shear zone. So this one is the primary deformation zone actually, right? The plastic deformation of metal in the shear zone is the primary deformation zone, as we have already shown here, right? So this one is the primary, not the secondary. So option C is also goes wrong. And then option D says plastic deformation of metal in the shear zone being the primary, that's correct. And then secondary is between tool and workpiece. No, so it is between the tool and chip, right? So this blue region here. So option A becomes the correct then. I hope that's clear. Okay, so this question says, what's the relation between the rake angle and the built-up edge actually? So you know what are the factors affecting built-up edge formation, right? So they are mainly low cutting speeds, okay, and then large feed and depth of cut, okay, then small rake angles, and then your high tool chip friction, right? So between these four options, which parameter matches? So a low rake angle gives rise to a built-up edge, correct? So option B is the correct option here. Now, this question says that discontinuous chips are caused due to, of course, right now we have discussed that it's a small rake angle. Okay, so there is a rubbing action. Okay, and there is a continuous chip generation that happens in case of a larger rake angle. Okay, that is a sharp tool. Now, these continuous chips are formed in the opposite case. So the small rake angle, option B, should be the correct option here. Then we move to which of the following is an important factor in solid phase welding. So here you have to look at the parameters which should be considered before we decide which type of welding we are going to apply, right? So these are not the factors which happen to be considered during the process. These are not in-process parameters. These are the before process parameters. Okay, so one of them is type of bonding, because all the other things are happening just during the process. Okay, so we have option B being the correct option. Depending upon the type of bonding, the material characteristics, okay, and then these are the particular parameters which will help us decide what type of solid state welding we're going to use. Okay, so option B becomes the correct one here. And then we have a numerical problem out of Taylor's tool life equation. So this is a pretty simple question. We have discussed extensive problems on such topics last session. So it says if the tool life has to be doubled, then according to Taylor's tool life, the cutting speed will be what? Okay. So you know this relation, VT raised to the power n equal to constant. Okay. So you have been told that n value is this, and your tool life has to be doubled. Okay. So if that happens, then what happens to the velocity? Just plug in the values. You use the T2 as twice of T1, okay, and then we put the value of n as 0.596, okay, and then using these relations, you can find out that the velocity for the required condition becomes 0.662 of 662 times of V1, the initial velocity. So option B becomes the correct one here. So next one is, what is the average heat percentage carried out by chips when heat transfer to the atmosphere is neglected? So that was discussed earlier. So that is 70%, of course. And that happens in the primary shear zone, okay, primary deformation zone. And then this question says, which of the following is not actually an example of solid state welding? So it says not an example, right? You know, friction welding is solid state welding, diffusion welding is solid state welding. This automatically becomes correct. So option D happens to be the correct option for this question. So, okay, I hope that's clear. So we'll move to the next question, right? Okay, so the next one was a question out of arc characteristics during welding. And then you have here that it says that the coefficient of friction is given as 0.5. Rake angle is 20 degree. Okay. And direct current welding machine, the linear process characteristics gives your open circuit voltage as 0.5 as 85 volts actually, and short circuit current of 680 amperes. Okay, so at a time when the measured current is 800 amperes corresponding to an arc length of 8.5 mm, and measured arc current then happens to be your 480 amperes. Okay, this is a condition and then you have been asked that corresponding to a length of 6 mm, your arc voltage and length characteristics has to be found out. Okay, so in that case, okay, so in that case, you look out to the solution. For linear arc source characteristics, your voltage is given to be is related to the open source voltage V naught and the short circuit current IS for this particular relation. Okay. Now it has been given that V naught is 85 and IS is actually not given, right? Oh, 688 is given. So then this equation then becomes 85 minus I by 8 to is V naught by is, okay, into I. So you plug in the value of V naught as 85, you plug in the value of is as 680, what is given here, this one, and then you find out this relation. That condition happens to be your V equal to 85 minus I by 8. Okay. Also, you know that you can represent the voltage characteristics in terms of arc length L through this equation, where A and B are the constants. Okay, now equating these characteristics of the voltage source of the arc source to what is given in the equation, we find out this relation. Okay, A plus B into L equal to 85 minus I by 8. Now, this is one condition given is at 8.5 mm of arc length and a current of 800. So this characteristic equation becomes A plus 8.5 B equal to minus 15. Okay. And for the condition of 6 mm and 480 ampere, it becomes 60. Okay. Now you use first and second equation, okay, and solve it to find out the constants A and B. Okay, you get B is minus 30, A is to 40. Plug into the characteristic equation, okay, V equal to AL plus B, or V equal to A plus B, sorry, and from that you can find out your required characteristic of the arc source for the given condition. Okay, so sorry, there is one mistake. Okay, so proceeding further. This is your last question from your assignment number 6. It says it happens to be a relation between a type of welding and the power source actually. Okay, so you can see there's a direct relation between induction and electric. How you can find out how you can get an induced electric current, okay, through an AC supply. So induction welding is an example of electric welding actually. So because electric current an applied AC electric current can give rise to an induced electric current in other body when kept close to it without even touching. Okay, so given that, having said that, we can proceed to some problems which will be solving out of our next, this current rate contents. Okay. So I hope you have no problem with the assignment questions from previous week. Okay, so if it is clear, okay, so we'll look to solve some problems out of our current uh, week contents. So I have a question for you that the first product obtained after the breakdown of ignots is called. So I hope farming was taught to you in the current week. And if you have looked into the initial lectures even, you can answer this question. So what happens to be a first product obtained after the breakdown of ignots? Okay. What's so before answering that question, let's move to some uh, explanation of what happens to a billet, a slab, a bloom, etc. Okay, so these are some short descriptions of what these terms mean actually in manufacturing industry. So what is an ingot? Actually, this is a very large casting product, okay? And generally has a rectangular shape, maybe square or any polygonal cross section also as per demand or as per the requirement. It has a hot top which helps in improved quality of the end product, okay? And is generally discarded after production. Okay, because it is a very raw product, and it has many impurities, but is a very important part for good ingot quality actually. So what happens is, from ingot, we then look into your blooms, billets, and slabs. Slab is generally is having a cross section in which the width happens to be at least twice that of its thickness. Okay, so I mean to say the cross section is less thicker and is much wider than that of a bloom. And what is a bloom then? It is generally having a square or rectangular cross section, and generally greater than 36 square inches or 230 square centimeters in length. Okay. Now, blooms are generally used in rolling material and manufacturing products such as pipes, rails, etc. And then one more thing is about billet. So these are usually made with the help of continuous casting machine, and generally have a longer length, okay, and cross sections that are same throughout the length. Okay, and so if we move to our question, it says the first product obtained after the breakdown of ingots is a billet. Okay, what is a billet? It is a longer product and having a uniform cross section throughout its length. So the correct option here is your billet. So we have another question out of these concepts, which asks when ingots, blooms, and billets and slabs are compared based on their weight. This is what we find. Ingots are heavier than blooms. Okay, so yeah, ingots are much larger. This is the first product. So of course they are heavier than blooms. Blooms are heavier than billets, yeah, because billets are having a smaller cross section than bloom and having a higher material volume. Blooms are having a higher larger material volume than billets. And then billets are again heavier than slabs because slabs are having much less thickness. So the volume they take happens to be lesser than that of billets. So in that case, we have all the three options being correct. So option 4 happens to be your correct option. Proceeding. I hope this topic is clear, right? If it is so, let's proceed to some problems out of your stress strain concepts. Think you have been taught your true stress, engineering stress, true strain, engineering strain, then your principal stress strain concepts, then uh, think about your material yielding, how a material yields, what are the theories behind that, Tresca and Mises theory, okay, your distortion energy theory, okay. So if these concepts have been covered by you, these problems will be quite a cakewalk for all of you. So proceeding, it says that the flow stress of a material is given by stress sigma as your strength coefficient K actually is 500, and then your true strain epsilon raised to the power 0.1 happens to be your strain hardening exponent, okay, if you know. Okay, and then the Young modulus of elasticity is 200 GPa. Block of thickness 100 mm made out of this material is compressed to 95 mm. Okay, so there is a compression in thickness, and then the load is removed. Okay, So what happens to be the final dimension of the block in NM? Okay, so give it a try, and then I'll share the solution with you. Okay. Okay, so let's proceed with the solution of this current problem. Okay, so for your reference, let's first let first know that your true strain is actually your natural log of original to instantaneous area. Okay, or if the length remains constant, as in this case, you have a natural logarithmic of original to instantaneous thickness. Really. So when the length is not changing, okay, now your flow stress sigma f happens to be your yield strength k, okay, multiplied by your true strain raised to the power n, being the strain hardening exponent. Okay, if you know these things, then you can find the final dimension through this procedure, that your true strain is again natural logarithmic of your initial to your final thickness, right? So the particular material or a block was compressed from 95 from 100 to 95 mm. Okay, so your initial thickness was 100 and your final thickness was 95. Okay, so that means the true strain becomes 0.05 approx, and then using your stress strain relationship which has been provided, you can find out the true stress. Okay, this happens to be your around 371.5 megapascals. Now, using Hooke's law, okay, up to elastic limit, up to elastic limit, your Hooke's law holds true. So sigma equal to modulus of elasticity into strain, okay, which is again change in dimension to your original dimension delta L by L. From that, you can find your delta L, okay. So using the delta L, if you know the initial length, you can find out the final length, okay. So the final dimension then becomes 95.18 mm, okay. So hope it is clear. Cool. Then let's proceed to our next question of the day. So the question reads out as the flow stress of a material is given by this stress strain relationship for a plastically deformed material, as you know, where the strain hardening exponent is 0.1. Okay, and then K is your strength coefficient, psilon is is a true strain, and then a rod of this material has a length of 200 mm. A compressive load is applied on the rod to reduce its length by 10 mm, and then the load is removed. If the Young's modulus of elasticity of the material is 250 GPa and the final length is 190.136 mm, then the value of strain coefficient has to be found out. Okay, so you give it a try and then we'll proceed to the solution. Okay. Okay, so let's proceed to the solution, guys. Uh, I hope this question was pretty much similar to your last question. And so I hope you guys have solved it, have been able to solve it actually. Now, if you look at the solution, it's pretty much simple. It is similar. It has to be solved with the similar steps as your last question. So you find out the true strain as your final length. The material, the rod is reduced in length by 10 mm. So the final dimension becomes 190. You find out your ratio of final to initial length. Remember, if it is thickness, it happens to be your uh, initial to final. If it is in longitudinal dimension, then it happens to be your final or initial. Okay. So in that case, your true strain then becomes minus 0.05. Now you use the stress strain relationship for the plastic deformation as K epsilon to the power n being the flow stress. From that, you equate it to your Hooke's law, okay, for the elastic portion. And then equating these two, you can find out your K, okay, because your delta L, your final change in dimension, okay, you can see that it is 0.1362, okay. So 0.1362, your initial length was 190 after a deformation of 10 mm from 200, and then you equate it to your this sigma naught by Young's modulus, where sigma naught or flow stress is given by K epsilon to the power n value. From that, you can find out the value of K, which is the strength coefficient. Okay. So if we move to the next question, hope this question is clear, right? These two questions which we discussed now are pretty much similar, just a little change in your uh, values and just a twist of the final uh, end result. Okay, so now if it is clear, then we move to your next question, which says that the true stress and strain diagram of a strain hardening material is shown in this particular figure. Okay. Now, first, there is a loading up to point A that is a stress of 500 megapascals. Yeah, 500 megapascal stress, this point A. Okay, corresponding to a strain of 0.5. Now, then from point A, there is a unloading up to point B. Okay, to stress of 100 megapascals. Given that your Young's modulus is 200, you have to find out the natural strain at point B, that is your epsilon point B. Okay, so let's try, then we'll discuss with you the solution. So you can see here that when the material is being unloaded, the unloading is not following the path same as that of your initial loading path. Okay, it is because the material is plastically deformed, and there is some of the strain which is recovered, and some part is again uh, completely unrecovered. Okay, so yeah, so give it a try. So your question says that the material is first loaded to 500 MPa and then unloaded to 100 MPa. Then you have to find out your strain corresponding to your point B. Okay. So you know that the slope of this line AB, okay, is elastic recovery. So you can find out the E as your AC by BC, okay, and the slope of this line, that is your you know that your sigma happens to be your Young's modulus into your strain, okay, to strain, of course. Now what does E becomes? Sigma by epsilon, okay. Now that is nothing but your slope of this line, AC by BC, okay. So using that, you find out E, okay, put out the E value, which is given here as 200 GPa, okay, and then what happens becomes your unknown part, your BC, 300. So you keep BC as it is, and you find out AC, which is then your 500 minus 100, that is 400. From that you find out BC, okay, and then what happens to be your strain at B. So the total strain up to C minus your the strain corresponding to BC, okay. So the total strain up to C, if this is your O, then your OC minus your BC gives you your strain at point B, okay. So this is nothing but your 0.498, okay. So I hope this problem is clear. So let's proceed to your next question. If you don't have any doubts, the next question says that your true stress versus your true strain relationship again is given by this stress strain equation. Okay, and then you have to find out the cross-section area at the time of necking for the particular test. If the cross-sectional area at the start of the test happens to be 100 mm square. Okay, so let's try. Your initial cross-section area is given. You have to find out the cross-sectional area at the time of necking. If you know what is necking, actually when the material starts to fail after the ultimate stress point is reached, that point corresponding to the stress strain loading curve of a material is actually called the necking point. Okay? Now, the initial cross section is given. You have to find out the cross section at the time of necking for a material which is following this given stress strain relationship. The K value of 1020 and strain hardening exponent N value of 0.4. let me show you the solution, right? So your the stress strain relationship which has been given to your question is like this. Your stress is related as stress coefficient K 1020, okay, and the N is zero point 0.4. Okay, now the question says the initial cross section is 100. You have to find out the final cross section at the time of necking. So what happens at the time of necking? At the time of necking, you see that your true strain becomes equal to n. And how does that happen? You equate the derivative of your stress with respect to strain equal to zero. Okay, at the necking point, the ultimate tensile strength point, and that finally gives you your epsilon t as being equal to n. Okay, uh, I hope understand that, right? If you got it, then your true stress then becomes your natural logarithmic of your initial area to final area, and that again becomes equal to your 0.4, right? Which you can find out using this concept at the ultimate tensile strength point, and from that you can find out your final area, right? As 67.032 mm square actually. Okay. Now, I hope this question is clear to you. If you have any doubt with this question, please ask me. Okay. If it is clear, then let's move to the next question. It says that a copper rod is given to you, okay, and the wire is of same length, but the diameter is double in terms of the diameter of a steel wire. Okay. Now both the wires are hanging and are stretched by some stretching force. Okay. Now your delta LC and delta LS are your elongation for copper and the steel wires respectively, and YC and YS are your Young's modulus for copper and steel. Okay. Now you have to find out what is the ratio of change in length or elongation ratio of your copper wire to steel wire if your Young's modulus for copper wire is 5 times the Young's modulus for your steel wire. You can take help of this information given to you. This is a typical stress strain curve, and this is a representation of some basic formulas and concepts related to that. Please give it a try, and then we'll show you the solution in a couple of minutes. So let's proceed, okay, to the solution part. So you can look at the various points over the stress strain curve for a typical material, okay, where your elastic limit is defined by E. Then up to P, you happen to consider it as the proportionality limit, which is defined by the fact that up to P you have your Hooke's law valid, okay, and up to P you find an elastic recovery, okay. Now your E dash represents your upper yield point, that is when the material starts yielding, and then your YP is your lower yield point when yielding stops, okay, and then you have your strain hardening coming into action, and your stress increasing much as compared to your strain, you are able to load the material to a larger extent as compared to the corresponding deformation. This continues up to n, where your necking point is reached, your ultimate strength of the material is achieved, and then the failure begins. Okay, so the n is called the necking point, and then b happens to be the breaking point, where finally the material fails. Okay, so s happens to be a permanent set point. Okay, if you unload the material from e, there are some recovered strains, and the other part is unrecovered and becomes your permanent set. Okay, so this part e happens to be your permanent set point. Now, these informations, this is the regular, your Hooke's law valid up to your proportionality limit. And then these are, the strain, to strain values, the ratio of change in dimension to the original dimension, then your yield, Young's modulus, which is actually coming out of your Hooke's law only, and you're replacing sigma as the ratio, sigma the stress, flow stress as the ratio of load per unit area, and then you are defining your strain as the change in length to length. Okay, so finally you find out your elastic modulus is PL by A delta L, and name it as equation 1. Now here your area, this is a wire, this is a cylindrical wire, cross section area becomes pi r square or pi d square by 4. Okay, the length of the steel is L, and the diameter is d by 2. Okay, it is given in this question actually that diameter of the copper wire is double that of the steel wire, isn't it? So if you have taken the diameter of the copper is d, you take half of that as that of the steel wire. Okay, so the area in that case becomes pi d squared by 16. Now for copper wire elongation, your delta L is equal to delta LC. Okay, Young's modulus is YC, and the stretching force, in that case, let it be P. In the other case, you take the corresponding values as delta LS, YS, and the stretching force is P only, because it remains the same, isn't it? The question says it is stretched by the same stretching force. So P remains same. Now corresponding Young's modulus can be found out as PL by A delta L. Okay, so that is for copper, and this is for your steel. In the question, it is given that the modulus for copper is 5 times that of steel. You equate this two, okay, and you find out the ratio. Okay, 105. So I hope that is clear. If it is so, we'll move to our next question. That is, the question says, in a typical stress strain curve as given below, point D and E are far apart. Okay, point D and E are far apart. If that happens, what does that indicate about the particular material? Okay, so we have already discussed what is D. D is your necking point and E is your failure point, right? Now, what does this mean if the distance is more? Yeah. So let us first look at what is called in detail about these particular points to explain this problem and any other problem related to your stress strain curve. Okay, this is a very important curve, and there can be questions from these during your UG as well as your PG interview questions, anything. Okay, so I request you to kindly have a clear idea of this curve about the material behavior under loading conditions. Okay, so you know what is the ultimate strength point D. Okay, where the maximum stress the material can withstand is reached. E happens to be your fracture point or your breaking point where the material finally fails. The ultimate strength point D and the fracture points E far apart means that your plastic region is much more. Further increase in this plastic, the line representing a plastic behavior of the material, so that your material happens to be ductile. Okay. Now, again, if these are closed, that means your plastic region is small. Means what? The material cannot withstand much stress as compared to strain, and it fails quickly, which means that the ductility is less. In other words, the material is a brittle material. Okay, you know this ductility, brittlity, malleability, lustrous. This has been discussed in the earlier classes. Now, this is the explanation. The same thing. So point D shows your plastic deformation and E shows your fracture point. If these points are closure, it means the material will fracture soon or the material will be a brittle material. If these points are far apart, the material will not fracture soon, so the material will continue to deform for more times. Now it will show the ductility property as a typical stress strain curve. If D and E are far apart, it means the material is ductile material. Okay, I hope that is clear. And if it is clear, then I would like you to probably answer me this question. Probably you know this. So Q is your upper yield point, okay, and P is your fracture point. Now tell me that why there is a drop in the curve just after the end of the upper yield point. Okay. Uh, can somebody give me the answer to this question? Please think a little and let me know. So no. So okay, so actually what happens is what do you mean by yield point actually after which the material starts yielding, okay? I mean the material starts deforming plastically, but then why there is a drop? The drop is because as the material starts to fail, there happens to be much reducing resistance to the flow of the defects, okay, within the material. So as a result of which the defect starts flowing easily, and the stress or strength of the material suddenly drops. Okay, now after that, again, slowly the strain hardening factor comes into operation. So probably that is your next question. What is strain hardening? So strain hardening is actually piling up of your dislocations, dislocation defect within a material, okay, which happens due to shifting of a plane of atoms from its own place, and hence you can see the movement of a dislocation in one way, and in other way you can say a slip between two layers of planes in the opposite direction. Okay, so as the dislocation starts to move and starts to pile up one above another, we find a hardening effect which leads to strengthening of the material. That is called a strengthening effect, and this phenomenon is called strain hardening. Okay? So I hope this concept is clear to you. If it is so, then let's move to some questions out of your rolling area. The rolling derivations and some corresponding example problems, I think, has been discussed in the lectures. Now, let us take up this problem. It says that a strip with a cross section of 150 cross 6 mm square is being rolled with 20% reduction of area. Okay, there's a 20% reduction of area and a 400 diameter of steel rolls are being used. Okay, this you can consider a too high roll mill, and then you have a shear yield stress of the material as 0.35 and 0.4 kilonewton per mm square before and after the rolling process. Okay, now you have to calculate your final strip thickness, your average shear yield stress during the process, the angle subtended by the deformation zone at the roll center, and your location of the neutral point theta n. Okay, you can assume the friction coefficient to be 0.1. Okay, so please proceed. You can actually consider that there are consider an average shear strength value here before and after is given. You can take the average shear strength and then proceed. Okay. So you know how to solve this kind of problems, right? You have to first find your theta value corresponding to the rolling process. Okay, the angle subtended at the roll center. You know how to find that out, and then you can actually use your formulation for that. Cos of this particular angle happens to be 1 minus of del H by D. So, or in other words, you can also take it directly from the geometrical point of view. Okay, now after you find out this angle, you use that to find out the corresponding constant called lambda value. Okay, if you have looked at the derivation of this process, you'd see that the intermediate step, a lambda value comes, which actually depends upon your theta. Okay. Now, if you do that theta, then you can find out your lambda, and then you can put it in the equation of your neutral zone pressure. From that, you can find out the corresponding location of the neutral point theta n corresponding to lambda n. Okay, once you have found that out, I think probably this question completes. Okay, so let's look at the solution. Rather, let's discuss the solution. So it says that as there is no widening considered, because actually in case of rolling, the widening or spread of the material is considered constant, is considered to not to change during the operation. Okay, so there is a 20% reduction in area implies a longitudinal strain only of 0.2 with consequent 20% reduction in its thickness value. Okay, so using that, your final strip thickness then becomes 80% of the initial, because 20% is reduced. Okay, so it is having a 4.8 mm of final thickness, right? So you can find out the average yield strength through the method I told a few minutes ago. You take the average of the initial and the final corresponding to your before and after operation stress values to find out your average, K average as 0.375. Now you can find out your theta value, that is angle subtended at the roll center, you know. So this is your roll actually, and this happens to be the angle subtended, okay. This one. Now you find that using this geometrical relationship. So then after substitute, the values to find theta is 0.775 radians. Okay. Now, before proceeding, tell me what is a neutral point? Actually, what do you mean by neutral point? If you are asked, then you have to know that a neutral point is a particular point in the rolling process when your strip velocity and velocity of the sheet which you are rolling becomes equal to the velocity of the roll. Okay, and the difference actually nullifies each other. So that is called as a neutral point, or in other words, no slip point. Okay, because the velocity becomes equal for both. Now, if you know the neutral point, now you can actually find out the value of the location of neutral point theta n using this relationship, but that requires no TF, you know radius, roll radius. Okay, you only need your lambda n value. So lambda n you can find out by this equation. Okay, you find out theta I, okay, corresponding to lambda I. Okay, you find lambda I corresponding to theta I, and then you put in lambda I value here. You know TF, TI, friction coefficient. You can find out lambda n, right? So you plug it this lambda n back here to find the location of your neutral plane. Once that is found out to be 0.023 radians, okay, that completes your question, isn't it? The location of the neutral point theta. So we can further proceed with this type of problems to find out your roll separating force and power required in the rolling process. So you know how to find out your roll separating force. You have to integrate the net force before the neutral point and after the neutral point. Okay. Now, once you have found out the neutral point, actually, let's find out the roll separating force by using a numerical integration method. Actually, you all must be knowing about Simpson's rule of integration. Okay, numerical integration. If you have some data points, okay, now you have to take a particular range, right? To find, you have to divide it to number of segments to get some data points, okay, before and after the neutral point location. So let us divide your initial like before your neutral point, let us take 8 segments of division, and after neutral point, let us take us 4 segments of divisions. Okay, so that means each segment has a magnitude of 0.00681 before the neutral point and 0.00575 after the neutral point. Okay, so corresponding to all these values, we compute the data after the neutral point first. So you know the equations relating to your pressure value before and after the neutral point. This has been derived in your class. Now you have the theta values corresponding to that. You find your y value. Okay, so you know what is the y value if this happens to be your strip. Okay, so this happens, this way goes your y. Okay, so you find your corresponding y value. and then you find the corresponding lambda value. Okay, you can use this particular equation, and then once you find the lambda, you can find your pressure value using the equation derived in the class. You can see we have taken 5 data points as we have divided into 4 segments after, and the same thing we do for the region before the neutral point. Okay, and then we integrate it to find out the force as P into R d theta. Okay, your pressure, okay, into your area R d theta. You do that for after the neutral point using 0 to theta n. Okay, if you know your pressure rises up to the neutral point, becomes 0, velocity follows the opposite profile. So this be the neutral point, and this becomes your after part, and this becomes a before part, after part, and this becomes a before part. So once you do that, you find out your total force. Okay, using this integration from 0 to neutral, P r d theta and theta n to theta I, P before d theta. Okay. So as I showed you, if this be theta n, so this becomes your before, and this becomes your after. Now, what happens is you just integrate. You did not literally integrate. They have found out using the formulas your p value. Okay, all the p values. You take r, roll radius is constant, right? So you take r outside. Okay, and you use the Simpson's rule, which is actually h by 3. H is your segment length, 100,575 here for after the neutral point part. H by 3, this is 100,575 by 3 into this equation. Okay, you I hope know from your Simpson's rule. So this is the thing. You find out the total force, and then I proceed to find out the force for the entire strip width, which is a 150 mm, to find out that the total force happens to be your 1909 kilonewton. Now you have to find out the driving torque, which happens to be mu r square into p d theta. Okay, so this happens to be your before, this happens to be your after. So you take the difference of both to find out your total driving torque. And the similar manner you do as you have found out your force values, similar manner you do to find out your torque value. Okay, once you know the torque, you can simply multiply that with your angular speed of the rolls. Okay, to find out your what is that called, power. Okay, so this happens to be a torque for unit width of the strip. This happens to be a total torque, and this torque into your omega. Okay, this torque into your omega twice of that for 2 rolls gives you the total power. Okay, and omega value, you can find it out always as because your RPM is given in revolution per minute, you have to convert it to the angular speed as 2 pi n by 6t. From that, you find out your 2.5 radian per second is your angular velocity, and then you can simply find your total power, 2t omega. Okay, twice torque into angular velocity. Okay, I hope this part is clear. So this pretty much concludes your today's session. We have pretty much covered the topics taught to you in the class, and these are the probable topics which can from which questions can be asked. I think you practice all these questions too, and that would help you in solving the assignment as well as final examination paper from these topics. Okay. Then finally, you may ask questions or doubts if you want.